Hi, I am Mr. Tan, and I shall be your guide for today's biology home-based learning lesson. Extending from the topic of biomolecules, today we examine the critical role that some of these molecules have in living systems. Yes, that's the role of enzymes. Now, many things can be discussed about enzymes, but today we shall just examine the following question. How might the concentration of substrate molecules affect the rate of an enzyme-catalyzed reaction? Some of you may say, I have forgotten everything that my Sec 3 biology teacher have mentioned about enzymes. So for the benefit of these people, Mr. Tan will do a very short recap before we come back to address this question. Let's begin. So what are enzymes? Enzymes are biological catalysts. Catalysts are substances that can speed up chemical reactions and remain chemically unchanged at the end of that reaction. In the case of enzymes, they are either made up of protein or RNA, which suggests that enzymes are three-dimensional in shape. Enzymes are also highly specific. To help you understand, here is a diagrammatic representation of an enzyme molecule. It has a specific region, we call it the active site. It is this region where substrate molecule bind to. Now you realize that the substrate molecule can fit quite nicely into the enzyme's active site, much like how two pieces of jigsaw fit together. This way of fitting is what we describe it as is that they are complementary to each other. That the shape of the substrate molecule is complementary to the shape of the enzyme's active site. Now, after binding, the catalysis would take place, and the substrate molecule gets converted into product molecules. Notice that the enzyme molecule remains chemically unchanged at the end of the reaction, just as all catalysts. So we're ready to come back to the question that we initially asked. How might the concentration of substrate molecules affect the rate of an enzyme-catalyzed reaction? Now, by concentration of substrate molecules, we are referring to the number of substrate molecules found in a unit volume. So it can be high concentration or low concentration. The rate of an enzyme-catalyzed reaction here just refers to how fast the reaction is taking place. So essentially our investigation here is asking the question of how does changing the concentration of substrate molecules affect how fast the reaction takes place. The independent variable would be the substrate concentration, and the dependent variable would be the rate of reaction. Now you may wonder, why are biologists interested in our investigation? Our investigation is important because many living systems involves enzyme-catalyzed biochemical reactions. One example is digestion. And having a good understanding of the dynamics between substrate molecules, substrate concentration and enzyme concentration allows us to make predictions about how fast these biochemical reactions would take place. So let's take a moment to zoom into a microscopic level. Here I have a test tube, and in the test tube I have some enzyme molecules and substrate molecules. You see, they'll bump around, and when they encounter each other and in the right orientation, substrate molecules can be converted into products. Let's return to our investigation. How do we go about investigating this question? One possible way is to set up many different concentration of substrate molecules in many test tubes, and we can then keep the enzyme concentration constant in all these test tubes. I have a diagram here to show you 6 different test tubes with equal concentration of enzyme molecules. So assuming these 6 test tubes have the same volume, and if you do a quick count, you realize that the number of enzyme molecules in each of the test tube is the same. There's 8 in the first one, second one, third one, all the way to the 6th one. There are 8 enzyme molecules. Now, I would prefer to see them as the number of active sites in each of these volumes within the test tube, okay, as opposed to enzyme, because active sites is more precise. It's because it is the region where the reaction takes place. So now let's put in the substrate molecules. If we were to vary, and we have 6 different test tubes here, we will put in 6 different concentration. The first one, I'm going to use 1 molecule of substrate to represent 2.5% concentration. So if we were to double this concentration, instead of 2.5%, we go to 5%, then it is just multiplying this 1 substrate molecule by 2 substrate molecules. So as you can see here, there are 2 substrate molecules in the 5% substrate concentration test tube. Can you make a guess how many substrate molecules would I put in if I were to double the concentration to 10%? Yep, you will have 4 molecules of substrate. If it's 20%, you get 8, 40%, 16, and 80%, you have 32 molecules of substrate. I'm going to fill in the table. 1, 2, for 10%, you get 4, 20% substrate concentration, you get 8, 40% substrate concentration, you have 16, 80% concentration, you have 32. So all is fine, but what I would like you to pay attention to is, in each of this test tube, could you count the number of unoccupied active sites? Should that substrate molecule bind to the enzyme active site? If you look at the test tube with 2.5% substrate concentration, given that there are 8 unoccupied active sites and just 1 substrate molecule, the substrate molecule has a very high chance of binding to any of the 8 enzyme molecules. That leaves just 7 of the active site unoccupied. If we look at the second test tube with 5% substrate concentration, there are 2 substrate molecules and 8 enzyme molecules. So the 2 substrate molecules are likely to bind into the active sites of 2 of the 8 enzyme molecules. That leaves you with just 6 unoccupied active sites. For 10%, 50%, 4 out of 8 of the enzyme will have its active sites being occupied by a substrate. That leaves us with just 4 unoccupied active sites. And the interesting one occurs at 20%. There are just as many substrate molecules as there are active sites. All active sites, okay, will be saturated with substrate molecules. They will all be bound to substrate molecules, okay, at the first instance. At 40%, there is an even greater number of substrate molecules, so it is almost guaranteed that all active sites would be bound with substrate. In fact, there will still be excess substrate molecules that has not yet bind to any of the active sites, since all active sites are occupied at that point in time. Needless to say, with 32 substrate molecules competing for just 8 active sites, all active sites would be occupied at any one point in time. So let's just have a quick summary. You notice that at low substrate concentration, where there are much lesser number of substrate molecules compared to enzyme molecules, there is the active sites are not saturated. However, at higher substrate concentration, where there are as many substrate molecules as there are enzyme molecules, the active sites are all saturated. At this juncture, I would like to bring our attention to the last row of numbers. Do note that when there are available active sites or unoccupied active site, it means that you can still add substrate into the solution and that the rate of substrate turning into products can be increased since there are so many available active sites waiting, I put inverted commas, waiting to accept a substrate molecule which it would then convert into products. On the other hand, when all the active sites are occupied, there is no point in adding more substrate molecules into the solution because at any time there are just no available active sites that would act on these additional substrate molecules. We therefore say that the turnover rate, the rate at which substrate is converted to products at high substrate concentration, cannot be increased further if you increase substrate concentration. So, if I were to record my table now in terms of the number of substrate molecules that can be converted into products per unit volume per unit time, if I look at the 2.5% substrate concentration test tube, then I would say there's just one substrate molecule that can be converted into products per unit volume per unit time, since there is only just one substrate molecule in the test tube. Likewise, at 5% substrate concentration, at any one time you would, at the initial rate of reaction, you would only have 2 substrate molecules converting into products. For 10%, you get 4, since there is just 4 substrate molecules. There couldn't be more. And at 20%, you would just have 8, because there is just 8 substrate molecules being converted into products by 8 enzyme molecules. Now, when it comes to 40% substrate concentration, here comes the catch, because there is just 8 available active site at any one time. Even having more substrate molecules in solution will not increase the number of substrate molecules that can convert into products per unit volume per unit time, since all the enzyme active sites are occupied. The same logic goes for 80%, and then you would only have 8 substrate molecules converting into products. So this brings us nicely to the last part of our lesson. Back to the question of how might the concentration of substrate molecules affect the rate of an enzyme-catalyzed reaction. What we just discussed about the number of substrate molecules that can be converted into products, that is a measure of the rate of an enzyme-catalyzed reaction. Now, before I proceed, I would like you to have a look at the y-axis label. Notice that it says initial rate. Why is that so? That is because in every test tube, say the test tube that we determine to be 40% substrate concentration, well, at the start of the reaction, it is 40%. But do not forget that after 1 second, 2 seconds has passed, and 3rd second has passed, the number of substrate molecules that is still present in the solution is decreasing as they are converted into products. Hence, after some time, that test tube is no longer 40%. In other words, if I want to plot this graph that you see here, we will need to set up many test tubes, each with a different substrate concentration. This would correspond to the values on the x-axis of this graph. This is similar to what we have discussed in the earlier example where we have 6 test tubes of varying concentrations. I hope that is clear. So let's come back to plotting this graph. So we had our 2.5% substrate concentration, and at that concentration, because there is just one substrate molecule that can be converted into products per unit volume per unit time, that would also give us a rate of, or rather an initial rate of 1. For the 5% substrate concentration, because there are 2 substrate molecules in the solution, despite having 8 enzyme molecules in the solution, the number of substrate molecule that can be converted into product is just 2. The same goes for 10% substrate. 4 substrate in solution, hence the fastest it can ever go is just 4. At 20%, there are 8 substrate molecules, just as there are 8 enzyme molecules. All 8 would be able to bind to the 8 active sites, and all 8 would be converted into products. Hence, the top rate, the fastest initial rate that can be achieved is 8 substrate molecule that can be converted to 8 sets of product molecules per unit volume per unit time. But at 40%, this is where it gets interesting, because despite having 16 molecules of substrate, there is just 8 molecules of enzyme, and hence 8 active sites that can act on these 16 molecules of substrate. The top initial rate that can be achieved is just 8 substrate molecules being converted to product molecules per unit volume per unit time. The other 8 has to wait until the first 8 are done. So the top initial rate that can be achieved is just 8 molecules. And the same logic goes for 80%. So at 80% substrate concentration, despite having 32 molecules of substrate in the solution, because there is just 8 molecules of enzyme, then the conversion rate of substrate molecules into products is limited by the number of available active sites, in which in this case it's just 8. The remaining 16 just have to wait. Thus, if I join the dots, I would get a line that looks like this. So to summarize, the essential features of this graph is that at low substrate concentration of between 2.5% to about 10% or 20%, substrate concentration is the limiting factor. It limits how fast, or the maximum speed at which the reaction can take place. And if you were to increase the substrate concentration, it can actually cause the rate of reaction to increase, since now the problem is not with the number of active sites available, the problem is with the number of substrate molecules that would convert into products. The second feature is the situation where there is a high substrate concentration of 20% to about 80% or beyond. At high substrate concentration, no longer is the substrate concentration the limiting factor, because you have an abundant number of substrate molecules. It is, however, the enzyme molecules that are limiting, because there is not enough active site to be able to convert substrate molecules into products at even higher rates. With this, we conclude this lesson. You can now move on to the exercises. Thank you.